Problem states chlorination is to occur immediately prior to storage in a tank from which water is drawn to meet local demands. We have a pH of 7, a minimum temperature of 10 degrees Celsius, a minimum and maximum flow rate of 6 liters per minute and 25 liters per minute, respectively. Chlorine residuals 1 milligram per liter, a tank size of 10,000 liters. We require 1 log inactivation of Giardia cysts. We have no mixing or baffling in the tank. So what is the required CT? What is the calculated worst case CT in this scenario? And if this does not meet the requirements, what could be changed? So first of all, what is the required CT? Well, we have CT tables that we can look to for that, but in order to look up the right number, we need to note that we require 1 log inactivation of Giardia cysts. We have a pH of 7. Our minimum temperature is 10 degrees Celsius, and we have a chlorine residual of 1 milligram per liter. So if we look to the tables, here we have a table for 10 degrees Celsius. We're at pH 7 here. We want 1 log inactivation of Giardia cysts, and our chlorine residual is over here at 1 milligram per liter. So we look in the table and we see that 37 milligrams minutes per liter is our required CT. So what is the required CT? Required CT equals 37 milligrams minutes per liter. Okay, so next question, what is the calculated worst case CT? Well, CT equals C times T. C is just my chlorine concentration, which is 1 milligram per liter. T, we have a tank here, and for time, we're going to use the residence time in the tank, which we've used theta before for. Theta is equal to V over Q. But before we just plug in the tank size of 10,000 liters for the volume, we have to recognize that the tank may not be full at all times. So if the tank wasn't full, then the volume that would be relevant for the residence time would be something less than 10,000 liters. So we have to make an assumption about what the minimum volume ever in the tank is. For our purposes, we're going to assume that V min equals 2,500 liters, or about a quarter of the tank size. And then Q, am I going to use my Q min, which is 6 liters per minute, or my Q max, which is 25 liters per minute? I'm going to use my maximum flow rate, 25 liters per minute, because at that flow rate, I'll have the least amount of time spent in the tank. So Q max equals 25 liters per minute. So if I put 25 here, I wind up with a theta of 100 minutes. Now, with my time at 100 minutes and my concentration at 1 milligram per liter, my CT would be 100 milligrams minutes per liter, which is greater than my required CT. But before I do that, I recognize it says no mixing or baffling in the tank. So what happens if water comes into the tank and doesn't spend the entire residence time in the tank? Because our residence time is our average amount of time that's spent in the tank, but some of the water comes into the tank and exits quicker, and some of the water comes in the tank and sticks around longer. The only way that we would have all of the water sticking around for the entire residence time is if we had perfect plug flow. The less plug flow like our tank is, the more likely we're going to have water enter and exit before the residence time is achieved. That water would not be disinfected. So we need to correct our actual CT by a baffling factor. Which shows a typical table that you would see of the various baffling conditions over here on the left, the ratio you'd use, the factor you'd use, and then the description. So for example, we said with perfect plug flow, which is very high length to width ratio, very good baffling. What we see there is this ratio is 1, and that's T10 divided by T. What that means is the time it would take for 10% of a pulse input to exit the tank divided by the total amount of time for all of the pulse input to exit the tank. So if you had perfect plug flow, you have a pulse input come in at the beginning of your tank. It takes the entire time before all of the pulse comes out at the end of the tank. That means T10 divided by T is 1. But if you had a very highly mixed tank, like a CSTR or a CMFR, then you're going to see some of the mass of that pulse come out immediately from the tank because it's mixed. So as soon as any comes into the tank, it's mixed and starts exiting. So then you see the T10 divided by T is just 0.1. So whatever factor we get here, we're going to multiply that by our actual CT. And you can see here this top one, this 0.1, is for an agitated basin with no baffling, which we don't have. We're not stirring our tank. But we do have single or multiple unbaffled inlets and outlets and no baffling. So our baffling condition is poor, and we're going to use 0.3 as our ratio. So now we say our CT equals 100 times 1, but then we're going to multiply by 0.3. And so we'll wind up with 30 milligrams minutes per liter. So our CT actual is less than our CT required. 30 is less than 37 milligrams minutes per liter. So our actual CT is not meeting the required CT. And the problem asks, well, what could we change if we wanted to meet the required CT? So some ways, if we want CT actual to be greater than CT required, we can either increase CT actual or we could decrease CT required. So to increase CT actual, we could either increase C, which is this number down here at the bottom. We could increase our amount of time we spend in the tank. We could add our baffling to increase our baffling factor. And so we could increase our C, our residual. We could increase baffling. By adding baffles, we'll make it more plug flow like. Or we could increase the residence time. Residence time is V over Q. So we could either increase E min, or we could decrease the flow, Q max. The other way we could do this is we could decrease CT required. How do we do that? Well, we need to either change the pH or change the temperature, because we can't change the Giardia inactivation required. So we could lower the pH, which would be adding acid, or we could increase temperature or heat the water. Neither of these two are ideal, and so typically the easiest things to do would be to either increase the chlorine concentration or increase the baffling as a first cut. So this just shows the process to go through in any of these chlorination problems. We're going to figure out our required CT using the tables, calculate our actual CT, in which we take into account the concentration, the time, and baffling factors, and compare the two.